Very good evening, everyone. So, hope you are very well. Today, as you know, we are going to study about our NCRT chapter 2, which is Electrochemistry, and this is theory part 1. So, let's start. Okay, so first of all, let's talk about our objectives. So, after attending this lecture, you will be able to describe an electrochemical cell and differentiate between galvanic and electrolytic cells. Okay, so this is the objective of today for studying this chapter, which is electrochemistry. So electrochemistry is, comes in the physical part of the chemistry, right? Where we study about different cells and their calculations. So, after attending today's lecture, you will be able to describe the electrochemical cell and what will be the difference between the galvanic and the electrolytic cell. Okay, so we will focus on these two topics today in this lecture. So, the topics to be covered according to the NCRT are the first is redox reaction, which comes under the section of 2.1 in the electrochemistry chapter. Then we will cover the electrochemical cell, which is the topic 2.1 in the NCRT textbook of electrochemistry chapter. Then we will talk about the cases of electrochemical cells, which comes under the section of 2.1, which is electrochemical cell. Then we will talk about the electrolytic cell and the galvanic cell. Then we shift to our next topic, which is galvanic cell, which is our 2.2 section in our NCRT textbook in this chapter. Then we talk about the electrode potential. This topic comes under the 2.2 section topic, which is galvanic cell in the electrochemistry chapter. And then we will talk about the working of galvanic cell, how it works. Then we focus on the topic salt bridge. Then what will be the functioning of salt bridge? We will talk about it. And then we will see what is EMF. Then how can we calculate the EMF for a particular cell, the calculation of EMF. And lastly, we will cover the cell representation topic. Okay, so this is a detailed topic-wise information which is here provided, which we are going to cover in this lecture, in the lecture of NCRT Chapter 2, Electrochemistry, Theory Part 1. So let's start first of all with our first topic, which is electrochemical cells, marked as 2.1. And in this, let's study first of all that what is redox reaction. So redox reaction, in the topic redox reaction, first we have to understand that what is oxidation and reduction process. What are these, how it happens. Okay, so oxidation is a process where in a reaction loss of electron happens. So you can also say that we have various definitions for defining the oxidation term or the oxidation process, but here in this chapter we will consider the oxidation as the process where the loss of electrons is carrying out. The next process to understand the redox reaction is reduction. Reduction is again a topic or a process in which the substituent in between the substituents, the gain of electrons is carrying out. Okay, so one of the element or atom is gaining the electrons from someone else, or maybe from from the electrons. So basically it is gaining the electrons and becoming either neutral or negative. And oxidation involves the loss of electron, and after the loss of electron it will become positive in charge. It will be having positive charge and deficient of electrons. Now the redox reaction, which involves the oxidation and the reduction taking place simultaneously. Simultaneously is important because in the redox reaction, if you break this word redox, here red means reduction, ox means oxidation. Okay, so reduction plus oxidation, that means both the processes of reduction and oxidation is carrying out simultaneously, is taking place simultaneously. That process in which both process of oxidation reduction taking place simultaneously is known as redox reaction. Now, if you see this reaction here given as an example of copper and the silver ions. Okay, the reaction between these two, you can see that copper is when it is reacting with the silver ions, it is converting to copper 2 plus, and the silver is after the reaction with the copper in the solid state converting to the silver, right? You can clearly see that the oxidation and reduction, as it is an example of redox reaction, the oxidation reduction both are happening simultaneously. How? So we define the oxidation as loss of electron. So here the loss of electron is happening in the case of copper. Copper here have Cu, okay, but have no charge. That means it is having zero charges, right? If it has one charge, it should be written here plus one. If it is having minus one charge, it should written here like minus one. But it has no charge. That means here zero is present. So copper has zero charges, and when it releases two electrons after the reaction with the silver ion, it is converting to copper 2 plus. What does that mean? That it has loses its electrons to gain the positive charge, which is 2 plus. Now copper 2 plus indicates that it has lost its two number of electrons. Okay, so in this process from converting copper 0 to copper 2 plus, the release of two electrons is happening, which is oxidation process, right? Meanwhile, the silver ions is converting from Ag positive to the Ag in the 0. Okay, so here we have Ag positive, and also remember that here 2 is present. That means two ions of Ag positive is present, and they are converting to 2 Ag, right? That means each Ag positive is converting to Ag. You can say that, right? That means each Ag positive ion is gaining one electron to convert into the Ag in the neutral form, right? That means totally the gain of two electron is happening in this process, and the gain of electrons is referring to the reduction process. That means it is the reduction process happening here in this reaction. So this is an example of redox reaction where the copper is undergoing oxidation when it is converting from 0 to plus 2, and silver is going under the reduction process as it is converting from plus 1 to 0, right? Now let's talk about electrochemical cell and its types. So if a redox reaction can be split into half reactions, one for the oxidation and one for reduction. So if you see that if you have a redox reaction, okay, we just saw an example for that. So if you have a redox reaction, you can split it into two half reactions. There is a specific reason why we are calling it half reactions, because only one of the process is carrying out in that reaction, either oxidation or reduction. Okay, one for oxidation and one for reduction. So it becomes possible to build a device when you do this, that when you divide or when you split the redox reaction into two half reactions, it will be helpful to make this possible to build a device to make a device which is called an electrochemical cell, right? Electrochemical cell. And by reading this line, you can clearly understand that electrochemical cell involves the redox reaction. Now, in an electrochemical cell, the oxidation half reaction, which occurs at one electrode, like anode, and the reduction half cell occurs at the other electrode. which we are calling as cathode. Okay, so here two terms are introduced, anode and cathode. uh Basically it is depending on the cell, that which kind of cell we are talking about, and depending on that, the anode is sometimes act like oxidation half cell and sometimes act like reduction half cell. Okay, but here in the case of electrochemical cell, the oxidation half reaction occur at the one electrode, and that electrode is the anode, and the reduction half cell will occur at the other electrode other than the anode, which is called as cathode. Okay, so there are two electrodes present in our electrochemical cell. One is anode, another is cathode. Oxidation occur at the anode, reduction occur at the cathode. Oxidation reduction is same. The concept of oxidation reduction will be same, like gaining of electron and losing of electron for reduction and oxidation respectively. Now, by separating these two half reactions, electron can flow through an external circuit from the anode to the cathode, generating electric current. Now, as we are talking about a cell, that means we are talking about some chemical energy, some electrical energy, or you can say current. Okay, so we talked about redox reaction, anode, cathode, electric current, electrochemical cell, half reactions. Now, when you separate these two half reactions from a redox reaction, the electrons can flow through the external circuit, which is, by a wire, you can say, from anode to the cathode. Okay, if we have an anode here and we have a cathode here, okay, they are connecting with a wire, and the current is flowing from anode to the cathode. Okay, this is cathode, this is anode. Okay, in the case of electrochemical cell, and the electron is flowing through this external circuit from anode to the cathode and generating the electric current. Now, this allows the chemical energy of the redox reaction to be converted into the electrical energy. As I said that here in the redox reaction, we have talked about redox reaction. Reactions mean something chemically is going on, right? So, in the electrochemical cell, we utilize the chemical energy to convert into the electrical energy for the further uses. Okay, so this allows this separation of two half reactions from the redox reaction so that electron can flow from the open circuit or external circuit, from the external circuit from anode to cathode. This allows the chemical energy of the redox reaction, which is happening inside our solvent, to be converted into the electrical energy, which will be useful in many ways. Now, let's see what are the types of electrochemical cell. How can you define the electrochemical cell in different ways? So, there are two types of electrochemical cell. First of all, the first one is the galvanic cell, and the second one is the electrolytic cell. Okay, these are the two types of electrochemical cell. That means these are the two cells which comes under the electrochemical cells, which follows the same concept of converting the chemical energy of redox reaction into the electrical energy. Okay, so under the topic electrochemical cell, which is our topic number 2.1 as per the NCERT textbook, let's define or let's see the difference between electrolytic and galvanic cell, which is the two types of electrochemical cell. Okay, so what are the difference between these two kind of cells? So let's define first of all our galvanic cell. So galvanic cell is basically the Gibbs energy of spontaneous redox reaction is converted to the electrical energy. So under the galvanic cell, we talk about the spontaneous redox reaction whose Gibbs energy is converted to the electrical energy. And meanwhile, the electrolytic cell having the electrical energy is used to derive the non-spontaneous redox reaction. Okay, so this is the main difference, that in the galvanic cell, we use the spontaneous redox reactions which we use to convert whose chemical energy we use to convert to the electrical energy. And in the electrolytic cell, we use the non-spontaneous redox reaction, or in the electrolytic cell, the electrical energy which is produced by the cell is used to derive the non-spontaneous redox reaction. Okay, now how can you define the spontaneous and the non-spontaneous reaction? You can think about, or you can talk about the Gibbs energy here then. So Gibbs energy, for if a reaction, the Gibbs energy is less than 0, that is considered as spontaneous reaction. That means that reaction can happen spontaneously without any external effort, and so. And the non-spontaneous redox reaction is kind of reaction whose del G is greater than 0. Okay, whose Gibbs free energy is greater than 0. Now, if you talk about the second point, in the galvanic cell, the oxidation half reaction. So this is the first time we are seeing the half reactions. So if you have a redox reaction, you can divide that in oxidation half reaction and reduction half reaction. So how the oxidation half reaction will look like? It will look like that. Y, let's suppose it is an element Y. Okay, it is converting to Y positive and plus electron. So what we define as oxidation, so oxidation is the losing of electrons. And here in this process, in this given reaction, what is happening? Y is losing its electron, right? It is releasing its electron. That means it is undergoing the oxidation process. So that means this process or this reaction or the half reaction is of oxidation half reaction. So Y is converting to Y positive because it has losing its one electron. That means one positive charge will come over Y. The next is reduction half reaction. Reduction half reaction is, let's suppose we have element Z other than Y. Z is one electron is adding to the Z to convert it to the Z negative. Okay, here we have negative. Let me erase the extra things. Okay, so here we have Z negative, Z negative. Some call it Z and some call it Z. Okay, so here we have reduction half reaction in which we have a Z or Z which is gaining one electron, adding one electron into itself and converting to Z negative, right? So Z plus electron will be equals to Z negative. Why negative charge? Because the Z has 0 already. It is already in 0 state, but it is gaining one negative or one electron. So one negative charge will come here on the G. So this is the process representing the reduction half reaction as per the definition we have seen for the reduction, which is gaining of electron, right? And Z is gaining the electron. That means it is undergoing the reduction process. Now, if you want to write out the overall cell reaction, how you can do it? You have to just add these two reactions. Let's suppose this is first, this is second. Just add these. So Y, here Y is here, Z is here. So Y plus Z. Okay, so when you are adding two reactions, their reactant side will add together and their product side will add together. Okay, that means you have this reaction arrow, and from the left hand side of reaction arrow, whatever there will be, you will add the first and second reactions part, and then at the right hand side, whatever there will be, you will add the part of first and second equations. Okay, similarly happening here, you add Y and Z and electron also, but here also like Y positive, Z negative, and electron is adding. So this electron will cancel out this electron, and the final overall cell reaction will become Y plus Z will give us Y plus and Z negative. Okay, so Y plus Z giving us Y positive plus Z negative. Okay, now this reaction is a spontaneous reaction and del G for this reaction is less than 0. Now, if we talk about the electrolytic cell, it is also having the oxidation half reaction and the reduction half reaction. Now, if you see here in the oxidation half reaction for the electrolytic cell, the Z negative is converting to Z plus electron. Okay, so it is also kind of releasing the electrons as per the oxidation. Okay, so Z negative, which is having negative charge, that means it is having one electron or one negative charge extra on it. So it just release one electron from itself and become neutral plus electron. Okay, so this is depicting the releasing of electrons as per the oxidation definition. So oxidation half reaction. If you see the reduction half reaction, in the reduction half reaction we have Y positive. You are adding one electron into the Y positive and uh, or converting it into the neutral. Okay, so positive charge, that means it has one lesser electron or one lesser charge or negative charge. So it will add up the one negative charge or one electron into itself and convert to the neutral state. So this is the reduction half reaction, that is adding of or gaining of electrons. Now overall cell reaction will be according to the similar concept, that you have to add the reactant side and the product side all together from the first and the second reaction. Now here at the reactant side we have Z negative, Y positive and electron. So Y positive, Z negative and the electron, and electron is also present at the product side, that will cancel out. And here at the product side we have Y plus Z. Okay, Y plus Z. So this is the overall cell reaction for electrolytic cell. Okay, for this reaction, this is a non-spontaneous reaction, and the del G, that is Gibbs free energy for value for this reaction, is positive, greater than 0. Okay, del G, if you can see that del G is basically minus NF E naught. Right, E naught is electrode potential, or you can say EMF of the cell, right? And you can decide the del G value according to the E naught for a particular cell, or the vice versa. Like if you know the del G, you can easily know the E naught value. So if you talk about the galvanic cell whose del G is less than 0, less than 0 means negative. So this value will be negative when the E naught value will be positive. Right, because here if it is positive, the whole value has already one negative in front of them. So the whole value will be a negative value. Okay, so del E naught will be positive in this case. And in the case of electrolytic cell where the del G is greater than 0, that means positive. And as per this equation, that del G equals to minus NF E naught. You can consider the E naught for the electrolytic cell if del G is greater than 0. If this is greater than 0 means if this is positive, what does that mean? That here at the right hand side, the E naught value, because N and F will be constant. F is Faraday constant, N is the number of moles interchanging. It can't be negative. The only changing value is of E naught. So if E naught is variable here, so it can be positive, it can be negative. But it is given that del G is positive for electrolytic cell. So if this side is positive, that means the E naught is negative. Okay, that means E naught is negative. E naught is less than 0, because if E naught will be negative, that negative and this negative already present here will get multiplied and become positive. Okay, so the overall del G value will become positive. So like that, you can determine the value or the charge, whether the E naught will be greater than 0 or lesser than 0 by assuming this, that del G is less than 0 for galvanic cell and del G is greater than 0 for the electrolytic cell. Okay, now if we talk about our next topic, which is cases of electrochemical cell, which we are studying under the electrochemical cells, which is topic number 2.1 in the chapter electrochemistry. Now the cases of electrochemical cell, that means we just study a case of electrochemical cell. So it is given that if an external opposite potential is applied in the galvanic cell, which is given in the figure 2.2a. So figure 2.2a is this one, figure 2.2a. Here you can see that we have a whole, given here two beakers. One beaker is containing the zinc sulfate, another beaker is containing the copper sulfate. Okay, zinc sulfate zinc sulfate solvent is having zinc sulfate solution is having this anode of the zinc. Okay, and copper sulfate is having this cathode as of copper metal. Okay, now salt bridge is connecting between these two solutions to make the electrical neutrality or the charge or ion neutrality between these two solutions, and these two anode and cathode are connecting with this circuit. Okay, so this is a potential here, you can see depicting by this arrow, right? Now here we have attached a instrument which measures the current. Okay, and here the electron is flowing from the anode side to the cathode side, and the current is flowing in the opposite way from the cathode to the anode. Now what we are saying that if the external opposite potential is applied in the galvanic cell and increased slowly, we find that the reaction continues to take place till the opposing voltage reaches the value of 1.1 volt. Okay, so here it is given that when your E external means the external opposite potential is lesser than 1.1 volt. Okay, that means you are providing the external potential whose value is lesser than 1.1 volt. So what will happen? The electrons starts to flow from the zinc rod to the copper rod. Hence, the current will flow from the copper to the zinc in an opposite way. And the zinc dissolves at the anode. Okay, zinc dissolved at the anode and the copper deposited at the cathode. So zinc anode is present in the zinc sulfate solution. So this zinc is kind of shredding from this anode and starts to dissolve in this solution. Okay, and the cathode here, the copper, because the cathode is already of copper, so copper starts to deposit on the cathode. Okay, so this is the process, and this is going to happen, and this reaction continues to take place when till the opposing voltage reaches the value of 1.1 volt. Now if the external potential will reach the value of 1.1 volt, that means when the external potential will become equal to 1.1 volt. So you can see that we have two solutions, the same structure, the same we have arrangement where the two solutions are here connecting by the salt bridge, zinc sulfate, copper sulfate, zinc anode, copper cathode, and we have the circuit connected to it, but the external potential is 1.1 volt exactly. Then what will happen? There will be no flow of electrons or current will be observed, and the no chemical reaction will also happen because there is no electron flowing, right? If no current flowing, no electron flowing, that means no chemical reaction will going to happen. Now, when the reaction stops altogether and no current flows through the cell, okay, so it is given that first of all, it is given that when you apply the external opposite potential to the these two anode and cathode connecting circuit, what will happen? The potential starts to increase slowly and the electron will flow from anode to cathode, and the reaction will continue to take place till the voltage which will reach the value of 1.1 volt. At the 1.1 volt value, the reaction stops altogether and no current flows through the cell. Now, any further increase in the external potential, okay, so Ex we are here representing the E external. Okay, now if you increase any further in this value of E external, again starts the reaction. This will again start the reaction which is just stopped at 1.1 volt. Okay, when you just increase the external potential from 1.1 volt to the more, what will happen? The reaction will again start, but in the opposite direction. Okay, as present in figure 2.2c. So C part is this. Similar structure, the zinc sulfate and the copper sulfate, the zinc anode and the copper anode, the salt bridge, the current is flowing from cathode to the anode. Now this time the zinc become the cathode because the reaction is reversed, and the copper become the anode and the current is flowing from cathode to the anode. Okay, and the electron is flowing from anode to the cathode. Okay, this happens when the external pressure will be greater than 1.1 volt. Okay, so electrons flow from copper to zinc and current flows from zinc to copper, and zinc is deposited at the zinc electrode and copper will dissolve at the copper electrode. This dissolving and depositing process will also get reversed. Okay, so here when the external potential is lesser than 1.1, the zinc is dissolving in the solution or dissolving at the anode, but the copper starts to deposit at the cathode, right? Here when the external potential is greater than 1.1, what will happen? Zinc is deposited on the anode, but copper dissolved at copper electrode. Okay, and at the exact value of 1.1 volt of external potential, there will be no reaction will going on and no chemical reaction will happen and no flow of current or the electrons will take place. So this is the figure 2.2 where the functioning of Daniell cell when the external voltage E external opposing the cell potential is applied. Okay, so this is the whole case we have just discussed for the electrochemical cell. Okay, now let's move to our next topic, which is marked as 2.2 as galvanic cell in our NCERT textbook of electrochemistry chapter. Now, under this topic, first of all, let's see that what is galvanic cell and what is its examples. So, galvanic cell is an electrochemical cell that converts the chemical energy or Gibbs free energy of a spontaneous redox reaction into the electrical energy. So, three terms are important here. First of all, we are talking about galvanic cell, which comes under the electrochemical cell. Secondly, it converts chemical energy to the electrical energy. And here in the galvanic cell, we talk about the Gibbs free energy of spontaneous redox reaction. Okay, spontaneous redox reaction means the del G will be negative and the reaction will happen spontaneously. Daniell cell discussed earlier is one such cell in which the following redox reaction occurs. So this reaction, zinc plus copper 2 positive, this will give us zinc 2 positive plus copper. So this is Daniell cell and we just discussed it earlier, right? In one of our cell in the previous slide. So this is the reaction which is happening there actually. So between the zinc and the copper ions. So zinc and the copper 2 positive ions are reacting with each other and converting to zinc 2 positive and copper. So zinc from the 0, it is going to 2 positive. So that means this is the process for oxidation, right? Zinc from 0 converting to 2 positive. That means this is the oxidation process. And copper from 2 positive converting to 0. Copper from 2 positive converting to 0. That means this is the process for reduction. Okay. And this is the NCERT equation 2.1 present in our NCERT textbook. Now, this reaction is a combination of two half reactions whose addition gives the overall cell reaction, which is this. Okay, now this is a redox reaction. As I just described, that both the oxidation and reduction process is happening in this reaction simultaneously. So this reaction will be the combination of two half reactions, one for the oxidation and another for the reduction. Whom if you will add, they will give the overall cell reaction, which is this. So the first is reduction half reaction, which is this one. So copper 2 positive plus 2 electrons converting to copper. So copper 2 positive from 2 positive converting to 0, becoming neutral. That means it is gaining electrons and the reduction is happening. So this will be the reduction half cell. This is NCERT equation 2.2. Now, if you talk about our second half reaction for this given cell reaction, it will be oxidation half reaction. What will be the oxidation half reaction? In the oxidation half reaction, the oxidation is happening. That means the releasing of electron will be happening. So zinc is releasing its 2 electrons and becoming zinc 2 positive from the neutral state. Okay, so zinc in the neutral state is converting to the zinc 2 positive and there will be the oxidation half reaction for this. Okay, this is oxidation half reaction. This is reduction half reaction. So oxidation half reaction here is NCRT equation 2.3, and when you join or when you combine these two reactions, these two half reactions, you can get the overall cell reaction, which is this NCRT equation 2.1. Okay, now under the topic of galvanic cell, let's talk about the electrode potential. So at each electrode electrolyte interface, there is a tendency of metal ions from the solution to deposit on the metal electrode. Now, what we are saying that electrode electrolyte interface, that means a interface. If you can see this diagram, the straight line is representing a interface between the electrode and the electrolyte. So here we have a solution. Here we have metal ions. We have metal, positive. These are metal ions, and this is the interface. That means this is the line, or this is the boundary between a metal and a solution, or you can say electrode and the electrolyte. Okay, so at each electrode electrolyte interface, there is a tendency of metal ions from the solution to deposit on the metal electrode. Now there is a tendency of metal ions present in the solution like this. These are the metal ions. They have their tendency to deposit on the metal electrodes and combine with them. You can see we have an arrow depicting this direction. That means this metal ion is going to deposit on the metal electrode to join here, right? And also vice versa, like this metal ion in the electrode is having a tendency to deposit or to be dissolved in this solution and become the one of the metal ion of the solution. Okay, like this you can see. Okay, so the at each of the electrode electrolyte interface, this process is happening, that the metal ions is having the tendency to dissolve or to deposit from the solution to the metal electrode. At the same time, metal atoms of the electrode have a tendency to go into the solution as the ions like this, which are described, and leave behind the electrons at the electrode. And here the electrons will left, and here the addition of new metal ions will be happening inside the solution. Okay, so the both metal ions which is present either in the electrode or in the solution, they have the tendency to go from one side to the another from the interface. Now at equilibrium, there is a separation of charges, and depending on tendencies of two opposing reactions, the electrode may be positively or negatively charged with respect to solution. So what we are saying, we are talking about the equilibrium state, that at the equilibrium time, at the equilibrium position, there is a separation of charges. It will depend upon the tendency of two opposing reactions. The electrode may be positively or the negatively charged with respect to the solution. A potential difference develops between the electrode and the electrolyte, which is called electrode potential. And due to all this, a potential difference will be develop between electrode and electrolyte. That means the metal electrode and the solution, metal ion solution. Okay, so the potential difference which will develop between electrode and electrolyte is called then electrode potential. Now let's talk about under the galvanic cell topic, that what is the working of galvanic cell. Now according to the IUPAC convention, standard reduction potentials are called standard electrode potentials. Okay, this is as per the IUPAC convention. They said that the standard reduction potentials are called as standard electrode potentials. The half cell where the oxidation is taking place is called anode and has negative potential. In the galvanic cell, the half cell where the oxidation process is taking place, that means the releasing of electrons is taking place at that electrode. So that electrode is known as anode. Okay, and it will be having a negative potential. The other half cell where the other process, which is reduction, is taking place is called cathode, and it will be having a positive potential, because anode is having, if anode is having negative potential, cathode will be having positive potential, because the two opposite processes are carrying on, anode and cathode. Thus, there exists a potential difference between two electrodes, and as soon as the switch is in the on position, the electron starts to flow from negative electrode to positive electrode. That means anode to the cathode. So this is how the galvanic cell will work. Okay, first of all, the standard reduction potential is considered as standard electrode potential as per the IUPAC convention. Secondly, the two half cells, first of all, the oxidation one, at which the oxidation process takes place, we called it as anode, and it will be having a negative potential. The second one, the second half cell where the reduction is taking place, we called it as cathode, and it will be having the positive potential. Because the potential is opposite of anode and cathode, there exists a potential difference between these two electrodes, anode and cathode. And as soon as the switch, which is connecting in our circuit, which is joining our anode and cathode together, so as soon as the switch is in the on position, the electron starts to flow from the negative electrode, which is anode, to the positive electrode, which is our cathode. Okay, so current starts to flow in the opposite direction, and the electron starts to flow from anode to the cathode. The direction of the current flow is opposite to the electron flow. As I said, if electron is flowing from the anode to the cathode, the current starts to flow. Okay, this is, so current represents by I. So current starts to flow from cathode to anode, always in the opposite direction to the electron flow. Potential difference between two electrodes of a galvanic cell is called cell potential, and it is measured in the volts unit. Okay, so as we are talking about galvanic cell, and the two electrode is present in the galvanic cell, they have different potentials and the opposite signs. So the potential difference which will be developed between these two electrodes will be called as cell potential, and it will be measured in the unit volts. Volt is represented by capital V. It is called the cell electromotive force, or EMF, of the cell when the no current is drawn through the cell. Okay, and when there is no current is drawing or flowing through the circuit or through the cell, this potential difference between the two electrodes of a galvanic cell is called as cell electromotive force, that is EMF. Now let's talk about salt bridge. In the previous diagrams, we have seen the salt bridge, right? So if you have these two beakers, they have their electrolytes and the electrodes. These two solutions, these two electrolytes are connecting together with this salt bridge, which is kind of alternate inverse U of structure. Okay, inverse U structure. Here, if you talk like outward, it is having something like this kind of structure. It is open from here. Okay, and all the other things are closed. Only the openings are open. Okay, so if you talk about salt bridge, an agar-agar solution generally made up of sodium chloride and potassium sulfate or sodium nitrate. So in the salt bridge, an agar-agar solution is present, either made up of sodium chloride or potassium sulfate or sodium nitrate. In this, inside the salt bridge, we can have these three type of solutions. Okay, so basically salt bridge is for maintaining the neutrality of the ions between the two solutions. Now, what is the functioning of salt bridge? How the salt bridge functions in a cell? So first of all, it will permits the passage of electric current internally. Okay, so if you talk about the circuit, it will be like two beakers and they are connecting with the salt bridge, and the two electrodes are connecting through the wire externally, right? And the current will starts to flow from this wire which is connecting our two electrodes, but it is through the external circuit, not inside our solution. Okay, but salt bridge permits the passage of electric current internally. It maintains the electrical neutrality of the solution, as I said, because both positive and negative ions, kind of dissolve or deposited over the anode or in the electrolyte. So the maintenance of electrical neutrality is must, and for that we use the salt bridge in our cell. It prevents intermixing of the solutions. Also, that's why it is maintaining the electrical neutrality, because it is preventing the intermixing of solutions. We can't, through this, the two solutions or the two electrolytes can't mix together with each other. It does not take part in the cell reaction. Okay, this is also an important point, that whether it is present in our cell structure, and also it is dipped in our solutions, electrolytes, it does not take part in the cell reaction. When there is oxidation, there is accumulation of cation on the left side. So when there is an oxidation process, releasing of electrons is happening, there will be the accumulation of cations on the left side. That means the left electrode. Or you can say we have this salt bridge. Okay, we have two solutions. So at the left side means this side. Okay, so when there is oxidation, there is accumulation of cations on the left side. And due to the reduction, there is accumulation of anion on the right side. Inversely, right? Whatever is happening in the cation or in the anode, the same opposite reaction or the same opposite process will happen for the cathode or the anion. Now, to neutralize the excess positive charge, anion from the salt bridge will flow into the solution. Now, what will happen? So basically, when there is oxidation, the cation will accumulate on left side. When there is reduction, there is accumulation of anion on the right side. And if you want to neutralize this excess charge or positive charge, the anion, which is of negative charge, from the salt bridge, it will flow into the solution to make the neutrality of the solution, to neutral that positive charge. To neutralize the excess negative charge, similarly, the cation from the salt bridge will flow into the solution. Okay, so the basic or the main thing which salt bridge is doing is that it is maintaining the electrical neutrality of the solution. If there is an excess of negative charge accumulate, the cations will flow from the salt bridge to make to neutral that negative charge. And if there is an excessive positive charge accumulation happens, the anion will flow from salt bridge and makes the solution neutral by neutral the positive charge. Now let's talk about EMF. EMF, which is electromotive force of a cell, is maximum potential difference between the two electrodes of a cell when there is no current is flowing in the circuit. So EMF, which is our electromotive force, EMF for a cell is a maximum potential difference between two electrodes which we are using for a cell when there is no current is flowing in the circuit of the cell. So it is a measure of cell's ability to drive the electrons from anode to the cathode through an external circuit. If you talk about the standard EMF represents by E naught of cell. Okay, this naught is representing the standard EMF. So standard EMF is the EMF which is measured when all the reactants and the products are in their standard states. Okay, that's why as the name says standard. So we use the standard EMF to measure the EMF when there is a conditions or the states of the reactants and products is standard. Like What is standard now? Like 1 molar concentrations, 1 atmospheric pressure, 25 degrees Celsius temperature, that means room temperature. Okay, these are the standard states. For a galvanic cell, the E cell, that means the EMF, the potential of the cell is equals to the E naught of cathode, the standard EMF of cathode minus standard EMF of anode. This is the way if you want to find out the overall potential difference of the cell. The EMF of a cell depends on the nature of electrodes, the concentration of solution, temperature, and pressure. These are the factors on which the EMF of cell will going to depend upon. First of all, what is the nature of the electrodes? Okay, either it is of metal, non-metal, acidic, basic, or reactive, non-reactive. Okay, so the EMF of cell will depend upon nature of electrodes, the concentration of solutions which we are using for the cell, and temperature which we are providing while the reaction going on in our cell, and the pressure which we are applying. Okay. Okay, now if you want to calculate the EMF, how can we do the calculation of EMF? So let's suppose if X is the reduction potential, then minus X is the oxidation potential and vice versa. As I said that whatever is possible or whatever is happening for the reduction process, the opposite process will happen for the oxidation and vice versa. So if X is the reduction potential, minus X will be the oxidation potential. The cell having greater reduction potential will get reduced, and vice versa is for oxidation potential. So if any cell is having the greater reduction potential, that means it will get reduced. Okay, and if it is having the greater oxidation potential, it will get oxidized. EMF of a given cell will be summation of reduction potential of reduced species and oxidation potential of oxidized species. Now, for a given cell, the EMF will be the summation. That means you have to add the reduction potential of reduced species, the species which are reduced, which has gained the electrons. Okay, so the reduced species reduction potential and the oxidized species, that means those species which have lost their electron. Okay, so their reduction potential and the oxidation potential respectively, you have to sum them, you have to add them, and that summation will be the EMF for that given cell. So EMF will be reduction potential of species getting reduced plus oxidation potential of species which is getting oxidized. Okay, now this is for cell reaction from under the topic cell representation. This is the cell reaction between the copper and the silver. So copper, when reacting with silver ions, it is converting to copper 2 plus and 2 silver, okay, in the neutral state. So copper from the 0 state converting to 2 positive, that means oxidation is happening, and the silver from the plus 1 is converting to the 0, that means reduction is happening, right? This is the NCERT equation 2.4 present in our NCERT textbook in the electrochemistry chapter. Now, if you talk about the half cell reactions for this particular cell reaction, the cathode will be 2 Ag positive plus 2 electrons. It will give us 2 Ag, right? This is the cathode reaction. That means at the cathode, the reduction process is carrying on, and in the reduction process, the species gets reduced and it by the gaining of electrons. So this Ag positive is gaining 2 electrons and becoming 2 Ag, becoming neutral. Okay, this is NCERT equation 2.5. Now, if you talk about the anode half reaction, on which the oxidation process is going on, so copper is converting to copper 2 plus, and it is also releasing 2 electrons. So releasing of electrons is happening. That means the oxidation is happening at the anode electrode, and the copper is converting from 0 to +2, and also it is releasing 2 electrons, right? So this is our NCRT equation 2.6. Now, for this cell reaction, the cell can be represented as copper, copper 2 plus, salt bridge, Ag plus, Ag. Okay, so this is the cell representation for the given cell reaction, where this double dash is representing the salt bridge, okay, between the two, you can say, electrodes. One is for the copper, another is for the silver. So this is the cell representation for this given cell reaction, and these are the two half reactions for this given redox cell reaction. And if you want to find out the electrode potential for the cell, this one, which is given like copper, copper 2 plus, salt bridge Ag positive to Ag. You can write it as E of right, that means potential of the right side minus potential of the left side. At the right side, we have Ag, silver, right? So we are talking about silver electrode. So E of Ag positive to Ag minus E of copper 2 positive and copper. Okay, so this is how you can find out the potential difference of the cell, which is representing by this representation, and whose equation or whose reaction is this. This E cell and this equation, whole equation, is NCRT equation 2.7 given in our NCRT textbook. Okay, so thank you very much for joining this session, and this is all for today's chemistry class.